And we continue. So now we continue with this third day, where Dominik is going to tell us about the Nash theorem, Nash embedding. Please continue.
So yes, let me continue where we left off. So we're trying to prove this easy version of Nash's theorem. It's easy in the sense that we're only considering one coordinate chart. So what we want to prove is we have a coordinate chart basically. So let omega smooth, open, bounded. Open, bounded. And my remaining metric is now simply a matrix field, the infinity map from omega closure to the space of symmetric n by n matrices, which are positive diagonal. And Nash says, and Nash says if two-dimensional is at least 2 and you give me a short map, and so this is my short map U, I take a smooth just to be to simplify even more. So smooth map which is short, co-dimension 2, so strictly short. And you give me an epsilon, which is zero. Now I want to find a map which is isometric, which is an immersion, which is epsilon close to U. So then there exists a solution of my PDE, which is a C1 map. Such that, well, it's an isometry. So induced metric is equal to the intrinsic metric G. And okay, in coordinates, this is simply the transpose of the Jacobian matrix times the Jacobian matrix of D. So this PD is satisfied, or the system of PD is satisfied, and I'm arbitrarily close to the map U, the short map, which I started from. And I told you guys yesterday, I explained to you the general philosophy that Nash. Question? So the general philosophy is I have a map which is short. I want to stretch it out, make it isometric. And Nash realized that the right way to do this is stretching it out iteratively. So you build strategy, build sequence UK. So these are smooth, strictly short immersions. Strictly short. Such that I'm getting less and less short. So every map, all the lengths are still short, but I'm getting less short, such that K plus 1 is less short than UK. I'm an immersion, I'm less short. I want in the end that, okay, I'm converging to an isometry. In particular, I want that the induced matrices or induced metrics converge to G. And in addition, I want that this sequence over here is Cauchy in C1, so that I can say there's a limit in C1, which is the C1 map. And because I'm converging, so these combinations of first derivatives of UK is converging to G. The same combination of first derivatives of D, of the limit of UK in C1, it will be G. So UK Cauchy in C1. Okay, and why do we do it iteratively? Why do we stretch it out iteratively? And maybe a cartoonish way on how to see this. So Nash realized that one good, like an ansatz or one building block, which you can use to stretch out the map, or one good building block to stretch out the map, is adding spirals. And what adding spirals allows you to do, so assume this is G. So I'm sitting in the space of positive definite matrices. This is my goal. I'm strictly short, so my map UK is somewhere over here. Or the induced metric, and I still want to go here. So what Nash realized is that when you add a spiral, you can increase the induced metric of a certain immersion in certain directions. So for example, I can go here, where from here to here, it's simply, let's say this is A1 squared eta1 tensor eta1. And from here to here, this is just a sketch, right? So from here to here, it's A2 squared eta2 tensor eta2. And Nash realized that adding spirals allows you almost to go from here to here, but up to a small error. So I can go from here to here, but I get a small, this is an O1 over lambda. So this building block which Nash introduced, this spiral, allows me to construct from the map UK a new map, let's call it V, such that its induced metric lies somewhere here in this red region. And because of this red error, I have to do this iteratively. So I cannot jump exactly from here to here and then from here to here by adding two spirals, but I can do this up to a small error. And so what Nash says is, okay, instead of going all the way to here and then all the way to here, I might overshoot with my spiral. So let's simply go maybe here, and then there's a small error up here. And then let's go from here almost to G. But I'm still short. And then I just repeat this process. So that's why I'm stretching out the map. I make it less short, but I still want to keep it short, simply to kind of go from here to somewhere here, and then from here to somewhere here. And in the end, I will end up in G. And the main question now is how to stretch out the map UK to be as close to G as I want, but still remain short. And as I said, the right way to do this is by adding spirals. So this was the stage. How to construct UK plus 1 from UK. We saw that adding spirals allows you to increase the induced metric by these little primitive metrics. So what you first want to do is see how far you are away from G. So you look at this distance, and then you decompose it exactly into a sum of these primitive metrics. Okay, you cannot only have two, but you can have a finite number, and this is what we proved yesterday in this decomposition lemma. So first, decompose G minus UK, E equals a finite number of primitive matrices, where these guys are smooth functions and these guys are unit vectors. Do not depend on x. So these are Sn minus 1 and AI squared are C infinity functions. On. And okay, then add perturbations. Or add n spirals. And I'm going to write down the spirals once more in the actual proof of this state proposition. I just want to repeat like the main heuristics. So add n spirals, and in the end, if I added n spirals to UK, I get a map which I call UK plus 1. And this map should satisfy that its induced metric is the same as the old, plus the small effect which all these spirals had, which say that I'm almost here, up to this small error, for every piece over here. What I get is the sum AI squared eta I tensor eta I, plus a small error. Which is very small if I choose the perturbation lambda, if I choose the frequency lambda I of the perturbation, which allows me to add the I primitive metrics, if I choose this frequency very large. Okay, and because I decomposed the metric defect over here into such a sum, I see that this over here is simply G minus UK star E. And so if I look at the induced metric of UK plus 1, I see, because UK induced metric cancels with this UK induced matrix, it's simply G plus this small error. And then in the heuristic, I said, okay, here we see likely a problem. What I did right now is exactly, I might have overshot, right? Because of this error term over there. If I add A1, I arrive here, but with the error, I might be outside. And then, okay, if I add A2, I might be too far. So how do we make this map UK short? It's very easy. So you simply do not go all the way to here, but you stop short. And how to do this is simply, instead of decomposing the whole thing over here, you decompose, let's choose a very small delta times the identity over here. So that you have some room. Now you see, if I decompose, okay, UK plus UK is strictly short. So this is strictly positive definite. So for a small enough delta, this is still a positive definite matrix. So I can subtract something, which then shows me that, okay, when I add all these pieces, what I'm adding is not the full G minus U star E, but I'm adding only, I'm subtracting some small delta. So in the end, what I get is that the induced metric of UK plus 1 is G, and then minus this small piece. And now I just simply choose the lambda i's over here so small that it's not bigger than delta, the identity. So I stay below G. Here I have something which is strictly negative definite. So simply choosing lambda I small enough or large enough, depending on delta, I will make UK K plus 1 strictly short. So let me finish this. So this is how we keep UK plus 1 strictly short. Simply going here, and then a small error keeps me within the bounds. So this is G minus delta identity plus all these errors. So if lambda I large enough, first of all, if I choose delta very small, still I'm very, very close to G. But I make sure that I'm on the right side of G. So then UK plus 1 good. So that's a strategy. And with this strategy, we hope to achieve this, the stage proposition, which I wrote down yesterday, just getting rid of the indices K and K plus 1. So let me just write this down again.
There is more white chalk.
Oh, thank you. So stage proposition. So what I hope to achieve with this heuristics is, given a strictly short map, given U is the infinity strictly short immersion, and epsilon and the delta, there exists a V. So this is UK, the V is UK plus 1. There's a V, which is still a smooth, strictly short immersion. Such that, well, first of all, I stay close to U. When C0, I'm less than or equal to epsilon. Secondly, I'm going as close to G as I want. So here, just to save some time, today I'm just writing V star E instead of dVt dB. I'm getting delta close to G for any delta, but I'm still strictly short. I'm not overshooting. And thirdly, because I need to make sure in the end that my sequence, so UK plus 1, is converging or Cauchy in C1. I want to control over the distance of the derivatives, between the derivatives. And what I already sketched you yesterday is that, roughly speaking, this distance is exactly the square root of how far the induced metric of U was from G, up to a constant, which only depends on the dimension. Square root, or some constant, which only depends on n and not at G. So that's what we want to prove with this heuristics. And then with this stage proposition, it's pretty easy to prove the theorem. Namely, you start with something which is strictly short. You choose a first epsilon, you choose a first delta. You get a map U1 with these properties. And okay, from there, I have a strictly short map. I can, here, I choose another one, epsilon 2, delta 2. I get another strictly short map with these properties, where now here I see G minus U1 star E. And G minus U1 star E is less than delta 1. And okay, if I choose epsilon to be going to 0 geometrically, delta as well, then this will be Cauchy in C1 and going to 0. I mean, the distance to G will go to 0. So this is the main proposition we have to prove, and this is the strategy. Decompose, add spirals, and make sure that these estimates over here hold. And let me recall the decomposition lemma, or the Nash lemma from yesterday. So what we saw yesterday is that this decomposition, which I just erased, can be done. So recall the corollary, which says that if I have a compact set in the space of symmetric positive definite matrices, for any k in symmetric n by n positive definite matrices, there exists a finite number, n, natural number, which depends on k, and unit vectors, eta 1 to eta n, and smooth functions, a1 to an, which are smooth functions. I think yesterday I just wrote on k, but you can choose them to be smooth function in the space of symmetric matrices, such that any matrix H in K can be written as a sum of primitive metrics. So let me write Li this time, and a sum with positive coefficients. So eta I and eta I for every H in K. And crucially, and for any H in K, at most, a finite number of terms in the sum are non-zero, and this finite number only depends on the dimension n. Doesn't depend on K. So this n over here depends on K, but if I look at a fixed H, only a finite number of these guys are non-zero. Only C, which is a C which only depends on n terms in the sum, are non-zero. And this dependence over here, I mean, the fact that I have we'll see this come out. So the dependence on the fact that there are only a number which only depends on the dimension n of terms which are non-zero directly translates on to this constant over here only depending on n. Otherwise, if you don't take care about this constant will depend on big N, and big N depends on K, and K will depend on U. So in the end, you will get a constant which depends on U over here, and this is really bad if you want to show that this sequence converges in C1 or is Cauchy in C1. So this is just this was just a covering argument giving the local decomposition lemma, which was simply a lemma in linear algebra. Like the fact that you can choose a basis of the space of symmetric matrices by exactly n star of these rank 1 matrices. And then you get linear maps which represent any matrix H in the space of symmetric matrices by in this basis. And then we had that if you're close to a fixed positive definite matrix, then in fact these coefficients are all positive. So you can take their square roots so that these functions AI over here are smooth functions. Okay, so that's the recap. Any questions? So now we have all the ingredients pretty much there. So let's prove the theorem. Unfortunately, because of space, I have to erase it. But I think by now it should be clear what we want to prove. Of state propositions. And okay, the strategy is clear. We look how far we are from D, we decompose, we add the spirals. Decomposition lemma is this one, or the corollary. What is the compact set K? Well, what do we want to decompose? We want to decompose G minus the induced metric of U minus this small piece, delta identity. So what is delta? Well, I had a delta in the proof of in the statement, just assuming delta or taking delta even smaller. So since U strictly full, there is delta identity room. So G minus U star E minus delta identity is still positive definite up to making my delta even smaller. Positive. Up to possibly making delta smaller. Sorry. Okay, now I have a nice, for every x, this is a matrix which is strictly positive definite. I have a compact set lambda bar. So if I look at the image under this map, smooth map, it's a compact set in the set of positive definite symmetric matrices. So then, and okay, give me a bit more room. Then K, which I define as G minus U star E minus delta halves identity of omega bar. This is a compact set. Okay. So I can decompose, or I can write this this symmetric matrix in this form. So G minus U star E minus delta halves identity is exactly. So let me be clear here. There exists an n, which is an n depending on k, and k depends in particular on U. U, G, like that. I don't care so much, but I want to just show you that one needs to be a bit careful, such that we can decompose into exactly n primitive matrices, ki squared, let me call it simply x, eta I, or AIX is simply AI. So this AIX is this AI evaluated as G minus U star E minus delta I parts identity evaluated as smooth map. If this guy is smooth, these are smooth. Okay, so I have my decomposition, and now I just add the spirals, one for each primitive metric. So this is one decomposition. And now true perturbation. Okay, I start with my map U, call this U0. Set U0 to be U. And iteratively, we add spirals. And for I is 1 to n, set ui is simply ui minus 1 plus ai divided by lambda I. And then I have my sign of lambda I x dot theta I. I have my unit normal vector field zeta I, and then I have a cosine lambda I x dot theta I psi I, where these frequencies I want to choose them. So lambda 1 chosen. AI are given, and okay, eta I are given. This is an I. And zeta I and psi I are simply unit normal vector fields to ui minus 1. And psi I are such that, first of all, well, they're units. They're orthogonal to each other. So, and they're normal to ui minus 1. So du I minus 1 transpose zeta I is the same as du ui minus 1 transpose psi I is 0. Okay. So I have a nice immersion over here. I have a nice n-dimensional submanifold in Rn plus 2. I have like 2 directions which I can choose. It's not so hard to show that you can find these maps over here. Okay, call F V to be Un. And now I want to show that if lambda I, lambda 1 to lambda n are chosen large enough, I can satisfy my 3 conditions over here. So lambda I shows lambda I large enough. Then 1, 2, 3, and short. Okay, it's the same computation I did yesterday, so I don't want to bore you with repeating it. But okay, maybe very quickly. So as yesterday,
a very pedantic question. Could it have been possible? I know just for playing around to have perturbed it somehow differently
definitely.
and successfully.
This one?
Yes, instead of spirals, could you have done something? Because those are the 3 that you need, but could you have used some other?
Yeah. I mean, so this is Nash's proof. He uses 2 codimensions already. If you want to do 1 codimension, you don't have 2 normal vector fields. You need to come up with something different. And what Kuiper did is simply adding waves. So it's a similar ansatz. You don't have sine and cosine.
Cool.
But the basic structure is the same. You have this AI in there, which corresponds to the decomposition into primitive metrics. You have some direction of your wavefront, and then you need some periodic functions which you let oscillate super fast, and you compensate this by making the spiral very small for the amplitude, so that in particular you're staying very close in Z0. Yes, but this is just.
Yeah, it's actually going very much to the point, like I was trying to make even with the local revolution. Somehow there's the right motivation and the proof just works. And like there's really something magical about kind of Nash uses 2 codimensions and spiral and it just works. So if you look at Kuiper's argument, it's actually more complicated. I mean, to make the, it's kind of got a stretching And it kind of, it's at least for me, I felt like slightly more complicated to kind of see. But as Dominik is saying, the critical piece is this kind of lambda one. You're adding high frequency stuff, but you're dividing by the frequency so that you're adding something which is small in C0. But when you take the derivatives, you get something which is order 1. And it's not just that the derivative is order 1, but the quadratic nature of the equation, the metric is quadratic, and that increases exactly in the way you want. It's super clever, but somehow super rigid, at least in this sense, to kind of get the pieces to work. So there's a geometric intuition, but then you have to get the estimates to work right. And so that's
yeah, to this quadratic nature. So this is also why this proof was so, or one of the surprising features of this proof is that you're solving a PDE, which is quadratic. You're solving du equals G, and one very plain approach would be first to solve linearizations of the PDE and trying to prove some kind of implicit function theorem. If you have a point which is if you know that you can realize this metric over here by an embedding, how does it look like in a small neighborhood? So kind of an implicit function theorem, and you would do this by looking at linearizations. But if you look at the strategy over here, if you look at the ansatz, the crucial point or the important piece which makes this work is the quadratic piece, which usually in these ansatzes over here, you would say, okay, quadratic piece is too small. Let's work with the linear piece. Whereas here, the linear piece we'll see is 0 or almost 0. So the linear piece would be something. I mean, if I do a perturbation of this one, the linearized equation would be the ut dv plus the wt would work with this one. But if you look at the nature of this one, because I choose zeta I and psi I to be normal to you, the leading order piece of this linearized thing is simply 0. Yeah.
It's like following the gradient where you're defining over here. So like increasing slowly with the restriction of Lagrange sort of restriction and following the direction in which you're increasing towards G.
I'm not quite sure.
Okay. All right.
But okay.
It's not a pedantic question at all, actually. It's kind of a very fundamental question. Kind of how do you make the perturbation?
So just to illustrate this, let me compute again. So du, what is the induced metric of ui? You have to compute the derivative of ui. You see the derivative of ui minus 1, and the biggest piece is when this lambda cancels this one. So derivative it's sine or cosine, lambda pops out, cancels this one. Everything else is as an O is a 1 over lambda. So here you have plus AI, you have the cosine, and then you have zeta I tensor eta I minus sine, and then you have psi I, eta I, and everything else is small. The derivative it's AI, I have a 1 over lambda. If the derivative it's zeta I for psi I have a 1 over lambda. So now if you look at the induced metric, so call this A, B, and C. Here you would see A on B, A on C, B on B, B on C, C on C. A on A is simply the old induced metric. A on B is exactly what I wrote down over here. So dut dw, this would be the linearization. A on B or A transpose on B is 0 because these guys are normal. So when A transpose hits B, I don't see anything. If A transpose hits C, I see a 1 over lambda. So if B transpose hits B, that's the quadratic part. This is large. So dw, the perturbation on itself, has a large piece, and this is the crucial piece which we're using to increase. So plus, and the crucial piece is exactly the this primitive metric over here, and everything else is a 1 over lambda. A transpose on A transpose on B, A transpose on C, B transpose on B, B transpose on C, C transpose on C, even as a lambda squared. Okay, so that in the end, the induced metric is simply U induced metric plus the telescopic sum I equals 1 to big N, and then UI minus 1. And here I see exactly this is AI squared eta I tensor eta I plus the small error. Plus sum I equals 1 to big N, AI squared eta I tensor eta I plus some error. And okay, I again deleted it, but we chose this decomposition such that this one over here is G minus U star E minus delta halves identity.
Red, not green.
Not red, but okay. So this one cancels with this one. I'm left with G minus delta halves identity plus sum. Okay, now in the first step, I choose lambda so large that every one of these errors, which I can make arbitrarily small by choosing lambda large, every one of these errors is less than delta fourth identity. So choose lambda I so large that O1 over lambda I is less than or equal to delta over 4n. N is this big number. So then if I take the absolute or the supremum over this guy, I see less than or equal to n times delta over 4n, delta halves. And I make sure that here, if this was, I mean, the worst case is that everything over here is positive definite, at most delta over 4n. So still this minus delta halves identity allows me to be shorted. So this implies that G star E is equal to strictly less than G minus delta over 4 identity, so short. And strictly less than G by this, or let me say less than or equal to. And secondly, if you look at the difference, G minus V star E is exactly delta halves plus all these errors. And G minus V star E 0 is less than or equal to, so this is same as delta halves identity minus all these errors. Sorry. And these I chose to be smaller than delta 4 over n. This is less than delta halves over n. So this is less than or equal to delta. Okay. So this is 3 or 2. Who is that? I'm delta close to G, but I'm still short. Because I didn't decompose the whole thing, I made sure to subtract some very small piece. The small piece depends on how close I want to get to G. Okay. What about 1? 1 is how close I am in C0 to the previous map. So also, you see that the distance in C0 is, this has size 1 in C0, because, okay, sine, these are orthogonal, I have sine squared plus cosine squared, so this is exactly 1. And so I see a bound by AI divided by lambda I. And AI is given, so AI comes from the decomposition of my map U. So I simply choose lambda i's large depending on AI. So choosing lambda I even larger such that AI 0 divided by lambda I is less than or equal to epsilon divided by n yields v minus u. Again, this is a telescopic series less than or equal to 1n ui minus 1. So this is less than or equal to n ai 0 divided by lambda I less than or equal to epsilon. This is 1.
Sorry, I'm trying to remember that you warned us about the condition, the dependence on the original U. We are allowed any dependence. So epsilon and so
Lambda is allowed any dependence at the moment, yes.
and that's fine. I mean, we
That's completely fine at the moment. It won't be fine after, I mean, it will be fine, but in a controlled way if we want to get more regular embeddings. But at the moment, it's completely fine. So what I warn you about is exactly, it's coming in now. When I want to estimate the distance in C1 basically. This clear? Okay, one is done. And so we're left to show that, let me just put this over here, dv minus du. C0, I want to show that this is less than a constant, only depending on n, and then g minus u star e square root. This is my goal, this is 3. Okay, but if you look at the derivative of v, so again, we want to do the same thing. Derivative of v minus derivative of u, we estimated kind of, I mean, we can write down what it is. So here we have to be a bit more precise, because if we were to do the same estimate as here, so say dp minus du less than or equal to sum from 1 to n, and then I simply estimate the distance between these two guys, I could get a good estimate over here, but I have an n over here. And I don't have a 1 over lambda again, which saves me. And so here I would see, so I don't have a 1 over lambda, which allows me somehow to choose to make something small depending on n. So here I would simply see in a good, I mean, straightforward estimate would give me something like n, and then the maximum of ai. But this depends on u. This depends on k, and k depends on u. So here we have to be a bit more precise. For 3, observe that dv minus du is the sum of all these dui minus dui minus 1 ls. So I can estimate this I plus 1 again. And now I go back to my one perturbation. I see that the biggest part is exactly this part, because everything else has a 1 over lambda. So these I don't care. Lambda large enough will make this small enough. But here I see the size of this is exactly ai. Again, this is size maybe 2 or 1. But this is a constant only depending on n. And here I see ai. This is less than or equal to sum 1 to n, and then ai of x. And then I have sum 1 to n, full 1 over lambda I. So this one I simply forget, because choosing lambda I small enough, I make it smaller than anything which I want. Right, this is the estimate I want. Here I have the lambda, which helps me to make this as small as I want. I simply choose it so large that I have less than cn halves times this number over here. And then I want to show that this one is also less than or equal to cn halves, or for some cn, which only depends on n. So let me forget about this. As small as I want. And why is this small? Well, it's because of the decomposition. I mean, why is it small? It's exactly this size, basically. Because I'm decomposing G minus U star E into a bunch of primitive metrics with coefficients AI squared and unit vectors eta I, eta I. So here from this equality over here, I simply take the trace of this inequality. When I take the trace, these are unit vectors. I see the sum of AI squared. And I see that the trace of this one is the sum of AI squared, is exactly the trace of this one. So in particular, AI, I can estimate it, or I can put taking.
Sorry, Dominik. If we would, I mean, I know it shouldn't be true, but if we would have gone back to the first lecture where you were mentioning the place where the metric does provide a counterexample, where this counterexample, I mean, where the argument would be breaking. So we could try to aim for the same thing. I mean, it's intuitively a subsolution. What's the name? Submetric. I don't know how to call it. What would be? Short. Thank you. Short. What would be? Where would the argument be breaking in the case?
So you mean in the case where I said we don't have a C2 embedding?
Yes, C2.
So very good question. Look at the sequence. I mean, look. So at this point, nothing breaks. Everything works. You can build these maps. You get a nice sequence which converges such that the induced metric converges to G. But if you look at this sequence, it's made from spirals, right? Adding these spirals is Q plus A divided by lambda sine lambda x on G, and then blah, blah. If you look at the second derivatives of V, you see the lambda coming out twice. So the second derivative of lambda is like second derivative of V is second derivative of U, and then plus huge lambda times A. Here, everywhere, I'm taking lambda even larger. I'm taking lambda large. So the second derivative of the sequence is blowing up.
Maybe I'm just trying to be testaruda. But what if you choose A over lambda squared? So, yeah.
Over here?
Yeah, right.
So lambda squared and put the lambda over here.
Uh-huh.
Then the correction which I want is not large enough. So here I get a 1 over lambda, and I will get a 1 over lambda squared. And this is, so choosing lambda large makes...
Right, so it's just this right size, so you are
Exactly.
far away. With
Yeah.
this.
So I have
Yeah, of course it's not true, but
no, very good.
Can I insist maybe on Sarai's stubbornness? If we would have allowed for an extra dimension and put instead of a spiral, I don't know, a double spiral or something like that, that could allow a second order, like instead of having like the cosine sign, insisting a little bit on the modifying the function. If we would have had enough space in the codimension, so we wouldn't have done this, but I don't know, something like this, and in the other direction, would have, I mean, would an adaptation of the same method with a different perturbation could have worked if the dimension was large enough?
So two things. Could have, if we just take the same approach, basically adding these spirals, but using the extra codimension. What you can do with the extra codimensions is adding multiple spirals at the same time, because you have more unit normal vector fields. Say you have 4 codimensions, you have 4 unit normal vector fields, you can add 2 cosine sine. Still, the second derivative of this guy is going to blow up, but it's blowing up slower, because I'm choosing less lambda i's. And okay, we'll see this maybe later, maybe tomorrow. But lambda I, so each lambda, so where did I write it? You have to choose this serially, right? And you choose lambda I large, also depending on lambda I minus 1. And okay, using these extra codimensions, you can make this second derivative blow up less fast. The other question whether you can think about a completely different building block. You could. And okay, so there are a couple of things you can do with more codimensions, and I just want to repeat what Govin said before. If you have a lot of codimensions, so if you have roughly n squared codimensions, so if you have something like q is bigger than or equal to I don't remember the exact.
Plus n plus, I think it's n star plus n plus 5, so that's not right.
That's the Günther.
Yeah.
Yeah, if you have a lot of two dimensions, so this is n squared already, roughly, and much more than Nash is doing. So then you can run a completely different approach, which is the second embedding theorem of Nash, and you can get actually smooth solutions, or as smooth as the metric is, CK metric. Something in between, which still, when the codimension is of order n squared, you can do other things which allows you to get more regular embeddings, and I think I want to talk a bit about this tomorrow. So let me hold on.
Yeah, but somehow, so I just want to stress that you are asking exactly the right question. So in some sense, like, with Sarai's question, like, you have to have the lambda 1 over lambda. That's the quadratic nature of the thing, so that you can't break. But somehow, what's happening when the second derivatives are blowing up in geometric terms is like you're losing curvature. That's what's really, like, if you remember where the rigidity theorems came from, it was kind of involving positive curvature. So what's happening with these embeddings is that they're rough, and so there's no curvature at the end of it. So that obstruction has been broken because you've allowed these kind of high oscillation. And somehow playing with curvature is kind of putting in fluctuations in different ways. So there are various variants, but somehow the building block over here is really kind of very robust, very clever, and kind of it just kind of it works. I don't know, it's kind of magical actually, but it doesn't look like anything else you've seen, and that's kind of the point actually. It's just a very original proof technique. So.
Okay, thanks for the questions. So we were about to prove to estimate the distance in C1 of these maps. I said, be a bit careful. This one is fine. And now here I'm crucially using the fact that in my decomposition, I had that at most a number which only depends on the dimension n of these guys are non-zero at every point x. So at most C, which is Cn terms non-zero at every x. So because then I can simply estimate the sum by Cn times the maximum of all these guys in C0. So hence dB minus du that's equal to Cn times the max of A minus 0. And then, okay, here I put lambda I large enough such that I'm less than G minus U star. So this is the second part, this sum, choosing lambda I large enough such that these errors over here are less than this one, which is a given quantity. So this is from the 1 over lambda I terms. Okay, now what is the size of AI0? On the other hand, the sum of AI squared x simply the trace of AI squared eta I, which is the trace of G minus U star E minus delta half identity from the decomposition. And okay, here I'm taking any norm, so let me take the maximum over all x. I take the maximum of the trace, it's some norm in a finite dimensional vector space. It's equivalent, so I can write that this is less than or equal to a constant which only depends on the dimension n times G minus U star E minus delta halves identity, whatever norm I choose. Maximum in x. And okay, this piece is less than delta halves, less than or equal to delta halves. If I choose delta small enough, in particular, delta halves is less than or equal to, equal to this one. So Cn, let's say Cn plus 1, U minus U star. If delta small enough, even depending on what I'm given, G and U. Okay, so taking any AI squared, it's less than or equal to the sum for any x. So I get the square is less than or equal to this, so I take square root. And I'm done. This is okay. And you do AI squared x less than or equal to the sum, these are all positive. AI squared less than or equal to this constant. Take the maximum, this doesn't depend on x, still less than or equal to, take the square root, still less than, with the square root. We get the square root. Then I adjust the constant, this constant. Okay, so this is a proof of the stage proposition. Simply decompose and add the spirals and check that when you choose the frequencies large enough, you end up exactly close to the map you started with. You end up close in C0, I mean as close as you can get in C1, and you increase the induced metric and almost achieve G, but you stay short. And now let me prove our theorem 1 using a stage proposition. Of simple Nash. Simple Nash was, I'm giving a strictly short immersion. I want to construct an isometric immersion, which is as close as I want in Z0 to the short immersion. And I simply iterate on stages. So given set U0 and choose epsilon is okay. Choose epsilon. So given, let me call this epsilon tilde. So the epsilon tilde tells me how close I want to end up to U and C0. This is the epsilon tilde and this is the epsilon in the theorem. This will be the epsilon in the proposition. I choose the epsilon in the proposition. So let me. And the proposition tells me if I give U, and then for every epsilon delta, I find V such that I'm closer to U, I'm closer than epsilon. My induced metric is closer than delta. And the derivatives stay V minus U star E square root close. Okay, I'm giving a strictly short immersion over here. I choose a first epsilon, let's call this epsilon 1. It's this epsilon over here, halves, say. I choose delta 1, which is simply 1/2 in the proposition to get V, which I call U1, strictly short, with U1 minus U0 in 0 is less than or equal to epsilon halves. G minus U1 is less than or equal to 1 half. And d U1 minus d U0 less than or equal to constant, and then G minus U. First application of my stage proposition, and now I just apply it again. I have another strictly short map. I can choose a new epsilon, I can choose a new delta. I will get another strictly short map. And I simply choose epsilon 2 to be epsilon over 4. I choose delta 2 to be 1 over 4. And okay, then repeat. Choosing epsilon k to be, okay, this is an epsilon tilde, sorry. To be epsilon tilde 2 to the minus k, delta k, simply to be 2 to the minus k. And it yields sequence uk, smooth functions, smooth, strictly short. Such that uk minus uk minus 1 less than or equal to epsilon k, which is epsilon tilde to the minus k. G minus uk star e less than or equal to delta k, which is 2 to the minus k. And duk minus duk minus 1 less than or equal to a constant which only depends on n. This is very crucial. It doesn't depend on uk minus 1. And now g minus uk minus 1 star e square root, which is simply c n and now square root of 2 to the minus k. Okay, so in particular, this is a summable thing over here. So uk is Cauchy in C1. In particular, uk Cauchy in C1. Since the sum Cn square root of 2 to the minus k is finite. Let's just do a telescope series. And I see that I'm Cauchy in C1. So hence it converges to some function d, which is a C1 function. And what does this V satisfy? Well, if I look, I have a convergence in C1. It follows that the induced metric of V, which is nothing but VV, because I'm converging in C1, it means all of the derivatives of the sequence converge uniformly to the to these derivatives of V. So here I can simply interchange the limit and differentiation. So this is the same as limit k plus infinity of duk duk. Because I'm converging in C1, all of the derivatives converge uniformly. And what is this? Well, if I look at this estimate over here, so this is the same as, so this this is the same as G minus limit G minus uk star e. And this is a thing which converges to 0. This is because of this. Because in some norm, this converges to 0, so it has to be converging to the 0 element. So V is an isometric immersion. And lastly, V is very close to the U which I'm started from, exactly because I chose this Maybe I have to do k minus 1 or so. So, and let's do over 4. And let's do over 4. Let's do minus 1. And E minus U less than or equal to the sum k equals 0 to plus infinity of uk plus 1 minus uk, which is less than or equal to epsilon t. Sorry. And then we're done. Okay. So this is the proof of the Nash-Pepper theorem, or the Nash theorem, in a simplified setting, where I'm not caring about different coordinates charts, and I'm not caring about the fact that I want to end up with an immersion, with an embedding, so injectivity. But you can imagine that if U is injective, I'm staying very close to U. So somehow, just by tweaking the right parameters, if I choose lambda large enough, depending on U, also because I have an estimate on how far I'm going with the differentials, you can imagine that you can make V to be injective as well. So maybe as an exercise. So that V can be chosen an embedding. I started with an immersion, I got an immersion. But if I additionally have that my short map is an embedding, so it's also injective, then the isometric map will be injective, or can be chosen to be injective. And the strategy again is just stretch out the view very systematically, add spiral and decompose, and add spirals for each primitive metric in the decomposition. And just computing, you see that you don't go too far in C1, because the leading order piece is A, and A came from the decomposition. And I'm getting closer and closer to G, so this one goes to 0 in a summable way. So this one is a summable series. And then I put G in C1, I have a limit in C1, I can pass to the limit in this equation and see that my limiting map is in fact isometric. Okay, any questions? Yes.
Maybe I'm forgetting something from the first lecture, but how easy is to find the very first short, the original youth? Kind of the seed system.
It's a very good question. It's not always easy. Sometimes it's easy because you're given already a map which is already embedded, or a manifold like S2. Put some metric on there. It already sits in R3. And as I said, if you're compact, you can simply shrink this embedding. So as soon as you have a topological embedding, you shrink it and you get a short one. The fact that there exist topological embeddings, this is a theorem due to Whitney. You can always find topological embeddings. So if Mn is an n-dimensional manifold, you can always find an embedding into R2n. I mean, topologically, this is a smooth manifold. I find a differentiable embedding into R2n, and I can find a differentiable immersion into R2n minus 1. So this is a very, very general theorem which you could use. If you're given a manifold, you know it's compact, use Whitney to embed it over here. Make it short simply by scaling it. And okay, in the general case, you can always, you can always build short maps. Sometimes you have to increase this this codimension over here. So Nash also, in his theorem, he also considers the non-compact case, and there it's a bit harder to construct a first short map because you cannot simply shrink it.
So is it case by case? Like
it's basically case by case.
but it's kind of like that's seen as the topological piece of the theorem.
Mhm.
So somehow it's also like at the time that Ash's theorem came out, there was a kind of lot of study of like these topological construction. So for example, projective spaces, I think the projective space is like the sharp one, right? It goes into R2 n minus 1. So there are n-dimensional manifolds that only admit a smooth immersion into 2n minus 1, right? Yeah, exactly. And like it's classified with kind of like these characteristic classes or something like there's an invariant that you associate manifold. So somehow like that's all that like in the theorem over here is really analysis in the sense that it's really the construction given.
metrics.
Yeah, but the existence of the initial condition is topological.
Okay, thanks.
Yep.
How would it look in the what is the typical shape that you would get in R2 and R2 and once you embed it, does it look like with a particular shape? Because you have been talking about what was the word that Govin uses? Singular, like I imagine it with a bunch of bumps or something like that. If you would to implement this procedure and take the limit and get a final U, does it look like bumpy?
Yes, very well. I mean, very.
Okay.
Yeah, but that's exactly the question that we don't know. In some sense, we know it should be rough because that's what the theorem tells us. But what it looks like and what is typical, actually, we don't like. It's also the case that, like, you know, there are very few pictures or numerical computations of these embeddings, even for two-dimensional manifolds. So we know they're going to be rough, but we actually don't know the critical how rough. We don't know the critical exponents. So that's kind of like.
Okay.
Yeah. No, but that's exactly the territory. No, that's kind of the point, right? Like we just don't know most of the stuff. Like we know this exists, but we just don't know its properties. Yeah, very, very so.
Interesting. So this is how this. I mean, this is the picture of the sphere by these French mathematicians. I don't know if you can see it, but it's very bumpy. So all these curves. So this is a case. Codimension is 1 now. So instead of adding spirals, you add waves basically, or corrugations. And so you see a very corrugated at every small level. So we're going smaller and smaller. The AI decreases because the AI is like this. So AI gets very small and lambda I is very large. I mean, lambda I grows and grows. So it means that the amplitude of the spirals along the sequence gets very small, very fast. So you see a first U1, which is not so corrugated, then you see U2, which is on top of this very much corrugated, and then you just add, and you go scale by scale. And then you see this thing, and you see that to get from point A to point B on the surface for a very tiny being takes a very long time because you have to cross all the mountains, all the ridges. And so you can make you can embed isometrically length preserving something which is very large, like a sphere, where you have to travel like thousands of kilometers, like the Earth, maybe a model of the Earth. You just shrink it down, and then you add all these small ridges. And that's how P looks like, basically.
And when you guys say rough, what is the
C1? Rough is C1, or C1 alpha.
Yeah, so actually, I think that's where we're going to go with this. So, you know, Dominik is going to tell you about kind of the results on C1 alpha, where basically he has the benchmark results on what alpha you can achieve. And so somehow it's C1, but so it doesn't have curvature, but it's got normals, and the normals are changing in a continuous way. So it's.
But you see that the normals, they go crazy. Like on a very small patch, the normal covers all the. You can imagine the normal going all the way on the sphere. So it's really bad in a sense if you measure the area which is covering in a small piece, the area on the sphere. But it has a continuous normal. Yeah, it's going very fast in all these directions. Okay. So I have a couple more minutes, I think.
You have like 10 minutes.
10 minutes. Okay, even though it's late, I think. We started at 5 or something.
Say?
I think we started at 5 or something. But okay, I'll try.
5 past 6? 5 past 6, you said? Or 5 to 6?
I think we started at around 5 p.m. or something. But I can try to finish it.
Then take more if you want.
No. I think it's.
I don't remember very well.
Yeah, it's okay. I don't want to bother you guys. But
Time is different here in the northern part.
say again.
Time is different here in the northern part of Mexico City.
Okay. Oh, it's also. I mean, it's late in the day. It's technical. So let me try to state problems and try to maybe then I go into this tomorrow. But where can you go from here? Now, Nash has this very nice theorem which tells you that basically isometric embeddings of class C1 are super flexible. Around every short map, you find a map which is length preserving. And we saw that in C2, you cannot hope to have this. C2, you have non-existence. In the case where you're two-dimensional sphere with positive Gaussian curvature, you have unique solutions in C2. And nothing like shrinking and still getting a length preserving map. And so the natural question is what happens in between? And this leads me to the threshold problem. Threshold. So let me state the threshold problem. Statement. And this is very much inspired by, okay, first of all, by this, just by the phenomenon, by this dichotomy. In C2, you're unique. In C1, you're super flexible. Natural question, what happens in between? And a tempting question or a tempting scenario to imagine is that you really have a sharp threshold such that above your rigidity of like positively curved two-dimensional manifolds, I mean, isometric embeddings of these guys into R3. And below you have flexibility in the sense of Nash-Kuiper. And this is very much, so this sharp threshold problem is very much inspired by the Onsager conjecture, which Govint mentioned on day one. And so what happened is that this iteration technique, which I showed you over here, which was invented by Nash, so what Gromov realized is that you can kind of put this more abstractly. And what he did is further developed this technique into a technique which is nowadays called convex integration. And convex integration allows you to prove, or it's proven to be a very powerful tool in proving a similar kind of flexibility of the space of solutions in certain other kinds of problems, in geometry and topology. But what Gromov also said is that you shouldn't hope for such flexibility to appear in problems which come from physics, because it's very unphysical behavior. What you get, these very wrinkly solutions, they don't make sense physically. And if I have a physical law, I would like to exactly know what the solution is doing. Therefore, it was very surprising that in fact this technique, or the technique of convex integration, was successfully applied by Camille de Ledis and Laszlo Seppellini to construct very strange solutions to the Euler equations, weak solutions to the Euler equations. And in fact, they showed that this technique has turned out to be, successful in resolving the Onsager conjecture, which let me recall that it says that if you have a weak solution to the Euler equations, incompressible Euler equations, there exists this regularity threshold, C1 third, such that above this C1, above this threshold, solutions they conserve the energy. So you have this extra conservation law, the energy conservation. Classical solutions, C1 solutions, they conserve energy. And Onsager conjectured, well, okay, also solutions which are on, so here's C1, here's C0. Onsager said in C1 third, everything, all the weak solutions which are more regular than C1 third, they conserve energy. Whereas here down below, you might hope to construct solutions or find solutions which dissipate energy. And in fact, the construction of these solutions, which was finally resolved by ICET in 2017, it's exactly, so it started over here. So Laszlo and Camilo, they constructed with the iteration technique very much inspired by Nash and super analogous. And they constructed continuous solutions which dissipate energy. And then this iteration technique was pushed further and further until in the end you got the Aussage conjecture. And so because of the similarities of the techniques involved in the proof, you might hope to have the similar kind of phenomenon for isometric embeddings. Isometric embeddings, flexibility in C1, rigidity in C2, thus there exists a threshold separating rigidity and flexibility. So this is the first threshold problem. And it's inspired by on-site conjecture. Rigidity, we have it mostly for two-dimensional positively curved. I mean, I'm talking about the Kohn-Foss and Hair-Loss theorem. So let M2 closed. So again, compact without boundary. Think S2, smooth, and G with positive Gaussian curvature. So you have rigidity of this thing in C2. So isometric embeddings which embed this manifold into R3 are rigid by convergent angles. And the question, and we know from Nash-Kuiper, such a thing you can always embed into R3 or isometrically immerse at least into R3. And you can shrink it because it's compact and you have flexibility, Nash-Kuiper, in C1. Thus there exists a threshold, alpha 0, such that we have the following dichotomy. If alpha is less than alpha 0, the Nash-Kuiper theorem holds in C1 alpha and 2 alpha. And what I mean is every short map can be uniformly approximated by isometric maps which are this regular. So there's C1 alpha, meaning every first derivative is alpha Euler continuous. And below, rigidity. In C1 alpha, above your rigidity. Rigidity for isometric embeddings from M to R3, which are C1 alpha. We know in C2 this is true. So if you have two such maps, they have to be the same up to rotation translation. I want to ask the question, can I lower this? So in C2 we're rigid, what happens over here? If someone gives me two isometric embeddings which are this regular, are they still the same thing? Whereas here I'm asking what happens over here. If I have a short map, can I approximate it by isometric maps which are this regular? And it turns out to be a pretty hard problem. And because it's a pretty hard problem, we started thinking about alternatives. So I will give you some results in already 10 minutes past. And
Take more.
I will give you some results tomorrow. Let me drink.
So it's an open problem.
So it's pretty much an open problem. So it's even not clear what the exponent is. So the question, when there exists an exponent, open. If there exists an exponent, what should be the right value of alpha 0? I mean, the analogy to Ansari's conjecture might suggest that this is 1/3. There are people who think it might be 1/3. There are people who think it might be 1/2, like Gromov, in a slightly general form. But it's at the moment it's open. We have progress, and I will come to this tomorrow. Let me state another threshold problem. So what's a bit what I don't like so much over here is that it's very specific to two-dimensional manifolds closed with positive Gaussian curvature. So somehow on-Sager conjecture is more about any solution of the Euler equation. But if you look closely, on-Sager conjecture tells you that you have the Euler equations, you have weak solutions, and then you have an extra piece or an extra conservation law, the energy identity, and your solutions either violate this or satisfy this. Here we're saying my solutions, the isometric embeddings, they're either completely unique or uniquely classified or completely wide. So we thought about if it's a better analogy to unsurrogate conjecture to think about, there should be something which is similar for isometric embedding, like an extra identity, extra PDE, which should be satisfied above a threshold and which could be violated below. And so let me call this a suitable, so this is a threshold problem. And this should hold for any remaining manifold into any Euclidean space. So let's take a compact. And Q bigger than or equal to n plus 3 or n plus 1. Thus there exists alpha 0 such that below alpha 0 you have some form of flexibility in C1 alpha. So for isometric embeddings which are C1 alpha from M into R cubed, and below alpha above, you have some form of rigidity. In C1 alpha. And let me state the conjecture by Gromov. So it's a bit, he kind of puts it more vaguely, but conjecture Gromov 2017 is alpha bigger or equal to 1/2 in threshold problem 2, 1. So what he says is that you should, in fact, not some form of flexibility, you should expect not some form of flexibility, but actually the Nash-Kuiper theorem in C1 1/2 minus for isometric embeddings into a suitable R cube. And let me state this theorem over here, which is a theorem due to Camilo and myself, 2000. So I don't remember when it was published, I think 2020. And then an extension by Metal Sau and myself, published in 24, I think, which tells you that alpha 0 seems to be true. Okay, let me state it like this. It's certainly true that this space, C1 1/2 is critical. And here, in a suitable sense, important. Okay, now I'm repeating myself. In a suitable sense, this means some form of flexibility, some form of freedom.
So it seems true in get more general.
More general is still not full generality, so we cannot handle full manifolds basically. But I can kind of tell you what this is about tomorrow. And what I want to talk about tomorrow also is this threshold problem 1. At least give you the best exponents which we have today and why they should be, why also. Okay, my plan for tomorrow would be tell you why you should hope to get Nash-Kuiper theorem in C1 alpha. What is a natural alpha which comes, which you could think of, and this is due to Borisov. It's called Borisov exponent. It's a very natural exponent which you could hope to achieve. Then tell you how Borisov, so Borisov didn't actually achieve it. It was then achieved by Camillo de Lellis, Sergio Conti, Camillo de Lellis, and Laszlo Seklikidi. And the basic strategy to get this, what you can do in 2 dimensions. In 2 dimensions you can do a bit better. And a very recent result, like a week ago, by Sau, myself, and Jonas Hirsch, that you can get actually a bit better than Borisov exponent. In particular, you get to the 1/3 in 2 dimensions. And maybe
Ok. Bueno, le agradecemos a Dominic.